This conference will now be recorded.
Very good evening, students. Today, in the last class, we had started with magnetism and magnetic materials. So here today, we'll discuss about bar magnet and solenoid equivalence, potential energy of a magnetic dipole, and we'll see how we can estimate the magnetic field produced by a bar magnet from the oscillation of a compass needle. So those things we'll learn. So before I start new things, today's topic, let me just recap what we have done yesterday. So we have seen that a bar magnet, even though there is no monopole, magnetic monopole, in the sense you cannot say there is magnetic charge, plus magnetic charge or minus magnetic charge. You cannot say like this, but still for a bar magnet, we have assumed that as if north and south pole are created by two opposite charges. Okay, so north and south pole, we have just thought of two equal and opposite charges are situated at these 2 points, north pole and south pole. Okay, this is say south pole, this is north pole, here it is minus qm charge. So magnetic charge, that's why this m is suffix m is. So if we have equal and opposite magnetic charges separated by a distance 2l, say this distance is 2l, so we can say that bar magnet act like a magnetic dipole. So bar magnet acts like a magnetic dipole, which has dipole moment m is equal to 2l into qm, 2l into qm or 2qm into l. So this is dipole moment. So this is what we had discussed yesterday. Just like electric dipole, in case of electric dipole, if it is electric dipole, then 2l distance into the charge of magnitude of the charge of the poles. Okay, so this is equivalent to electric dipole, and we just tried to see if electric dipole, if we consider magnetic charges just like electric charges, then we use just Coulomb's law to find out electric field. Okay, to find out electric field, and here also equivalently we are using Coulomb's law, kind of Coulomb's law, to find out magnetic field. Suppose the north pole produce, suppose this is r distance away, so this north pole will produce a magnetic field at this particular point, suppose bn. So this can be written as q mu by 4 pi epsilon naught. This factor is for magnetic field, and this is qm by r square. This is what I'm using here. Using that, we wanted to find out magnetic field produced by a bar magnet. We had already seen, and what is the magnetic by a bar magnet on its axial point. So let's look, if I just recap, suppose this is a bar whose charges, whose dimension is 2l, actually length is 2l, as you know, as you see from here. And see, at any point, axial point p, we have to calculate magnetic field due to this bar magnet. So what we do, just like electric dipole, as I said, we are using the concept of Coulomb's law only. Okay, concept of electric field itself. So I can treat these two magnetic charges as two separate magnetic charges. Okay, just like electric dipole. See, electric dipole, we had while calculating axial field and equatorial field, we just considered individual charges, and we had calculated electric field produced by each pole on each charges, each charge, and then we have just taken the resultant of that. Okay, so here also, if we want to calculate magnetic field at P point, then what we have to do, we have to consider that there is a positive QM charge here and there is a negative QM charge here. Now suppose the magnetic field produced by the north pole is Fn. Fn could be written as, see, this point P from this particular point. So Fn, in the sense, the field produced by north pole can be written as mu0 by 4 pi, then Qm by this distance. Okay, this distance is, see, this is r minus l whole square. And how, like, in which direction it is acting? It is acting from N to P. It is actually towards N to P. Okay, now similarly we can find out the field produced by this south pole where negative QM charge is there. So I can write here minus Q by 4 pi, sorry, mu0 by 4 pi QM divided by r minus l whole square. And this is this direction is from P to S. Field produced by south pole will be in the opposite direction to the Fn, as you see here in the figure. This will be towards S. Now if you want to find out see the axial field, now axial magnetic field, what I have to do, I have to just take the difference of this. Okay, since it is in the same straight line, so I can just take the scalar differences. That is also fine. I can just subtract. So mu0 by 4 pi into Qm, I'll keep together, and here it will be, see, r minus, this will be r plus l, sorry, r minus l whole square. Okay, minus of 1 minus r plus l whole square. So this is the whole term. I'll just write it here so that I can mu0 by 4 pi Qm, let it be here. So what I have here r minus l whole square, oh sorry, minus r plus l whole square. One over r plus l whole square. Okay, so this is the thing is that, so if we solve this thing, you know what you will get? You will get here 4 RL, 4 RL divided by r square minus l square whole square, and first term is the mu0 Qm by 4 pi. This is as usual. So now look, we know that magnetic moment M is equal to 2L into Qm. So this term we'll just take out. So 4 RL. So from there, see, I'll write 2 mu0 by 4 pi. This is 2L Qm into R divided by this R square minus L square whole to the power 2. This is okay. So this 2L Qm, this could be written M as well, right? This I will write M. So finally what we get, 2mr. So this 2 also I can just erase. So there is an approximation. See, if this distance r is much greater than the dimension of the dipole itself, then see this term here, this l square could be neglected, and see this whole term could be written like this. 2mr is fine here, and it is r to the power 4. So this r and r to the power 4, one power will get cancelled. So finally what we'll get, mu0 by 4 pi into 2m by r cube. So this is with approximation. Okay, this is with approximation, 2m by r cube. And you can see the field, what we are getting axial field, it is actually directing from N to P, or in the direction of the dipole itself. See, magnetic dipole always the direction is actually from negative to positive. So here the dipole moment M will have direction like this. Will have direction from S to N, or N to P, this direction. And here also we see the axial magnetic field in the same direction as the dipole. So this is very similar to the electric dipole, what we have seen in case of electric excuse me. So as you have seen for electric dipole, so similar things is acting here, or similar thing will get here. Okay, so bar magnet can be considered as just like an electric dipole. Okay, but I can just make you remember that QM, this magnetic charge, does not exist in reality. Does not exist in reality. Okay, does not exist in reality. We'll see from the magnetostatics when we have, I think we have here in this chapter. So magnetic Gauss's law for magnetostatics, there we'll see B dot dl, sorry, B dot ds, B dot ds, this will be equal to 0. Okay, so B dot ds will be 0. This means magnetic monopole does not exist. So that we'll see. Okay, now we'll see. Okay, magnetic field at an equatorial point. So how I have taken equatorial point, I'll tell you here. See, this is the bar magnet and this is the length. If I just bisect this bar magnet, okay, if I bisect perpendicularly, suppose this is in the plane and then I'm just taking vertical line like this. So this is bisecting the bar magnet, and I take at any point, at r distance away from the dipole. Okay, from here to here the distance is r. Okay, so I have to find out magnetic field due to a bar magnet where at any point on the perpendicular bisector of this dipole. This is called an equatorial point. So see, in this case, similar to electric dipole, as I said. So here also what we can do, we can actually find out magnetic field produced by the north pole at this point P. So that is obtained as, see, mu0 by 4 pi, this factor will be there always, just like 1 by 4 pi epsilon 0 in case of electrostatic. And then magnetic field is qm by x square. Here it is actually x, say x square, and x square is, you can see x square is equal to r square plus a square. So this is L, this length is L because the dipole is of length to L. This is r, this distance, suppose this is O, from O to P, OP is r distance. Okay, so that's how we can find out x is equal to square root of r square plus h square. We can just put this directly here if you like. Okay, now similarly, so this, but one thing is important here, the field direction is actually from N to P, and you can see this, okay, like this. This is important. Okay, now fs also has same thing, by magnitude they are same, qm by x square. So this is nothing but okay, so these are by magnitude, but uh, see, this fs is acting this way, p2s, right? In this direction it is acting. If it is acting in the p2s direction, then I have to actually see, if I just see this angle theta, then this angle will be also theta, and also this angle, if this angle is theta, then this angle is also theta. So I can actually break the component of this Fn into two. See, I can break the component along one along horizontal direction, another along vertical direction. See the vertical direction like this. Okay, so Fn sine theta I can say one component. Okay, Fn. Now see Fs in this direction. See they are by magnitude they are same actually. Only thing is the direction. So here we can see Fs. If I break into two. See for Fn I can break the horizontal component in this direction Fn cos theta. And see for Fs also, since this angle is theta, I can break two component, this Fs into two component, one along this direction, so which is Fs sine theta. Okay, Fs and Fn both are actually equal in magnitude. Equal in magnitude, this theta are also same. So that's why, so this vertical component Fn sine theta cancels Fs cos sine theta. Okay, Fs sine theta. They will cancel each other. All right, so they will cancel each other, and then what we will have? We will have only the horizontal component. See, for both cases, the horizontal component is in the opposite direction of the dipole moment. Dipole moment has direction this, okay, but this is in the opposite direction. See, Fs plus Fn, so cos theta. So cos theta components will be there. Okay, so if I just do it here, so the net magnetic field equatorial, this is Fs cos theta plus Fn cos theta, and both are same, so I can write 2 into Fn cos theta. So I can write this as 2 into Fn is, like mu 0 by, this is mu 0 by 4 pi, and this is qm here, and this is r square plus l square. This is the thing here. And what about cos theta? See here, from there cos theta is in this part divided by this, so base by hypotenuse. Base is x, I'm sorry, hypotenuse is x, base is l by x, l by x. What is x again? X is, sorry, r square plus l square, r square plus l square. So this is the thing. Now see, from here I can write 2qm into l, so this is nothing but m, and see mu 0 by 4 pi, and this part, see, l by r square plus l square whole to the power 3 by 2. Okay, now see 2qml, this is actually magnetic moment m, so mu 0 by 4 pi m. So there is okay, so this l will not be there, so this part is done. Now we'll just straight 1 over r square plus l square whole to the power 3 by 2. So this part, see here also we'll just do this approximation for a very short dipole. So l is much less than this, the distance where we are calculating the magnetic field due to the bar magnet. So at this condition, we can say r square plus l square whole to the power 3 by 2 nearly equal to r cube. Okay, so this equation now becomes mu 0 by 4 pi m divided by r cube. So you can see in the equatorial plane, see in the axial magnetic field, what we have seen, axial magnetic field, axial magnetic field was B axial was 2 mu 0 by 4 pi 2m divided by r cube. Okay, and this was actually along the direction of m. Okay, along the, if I write magnetic like vectorially, this is along the direction of m. Okay, so I'll write this direction of m, along the direction of m. Okay, but here you can see in case of this I have see half of this, and in which direction this is, just in the opposite direction. So I can write here, see, I can write for equatorial point vectorial. So this is first of all half of this, so we have mu 0 by 4 pi then m by r cube. Okay, and with a minus sign m cap. Okay, so this is the thing. So you can see that I can write the magnitude of equatorial will be, or I'll write in another way, axial mod of that, okay, will be 2 times of the equatorial magnetic field. So sometimes there may be a question, what is the ratio of this? Okay, so 2 times the equatorial magnetic field. Okay, all right, so we have seen how, see, in this case, see, this is actually completely analogous to electric dipole. So that we have already seen and we have discussed already in the previous chapter. So electricity chapter, sorry, electrostatic chapter. Now what we will see, bar magnet as an equivalent solenoid. See, bar magnet and solenoid, they are actually equivalent to each other. How? First point I can say, if you see, first of all, you know, I hope you remember, so solenoid is actually coil of a large number of coil of wire. Okay, so what you can do, you can just take an insulated wire, thin wire, copper wire, then you can just take any kind of core material like PVC pipe, or maybe a rod of iron, soft iron, etc. You can take, and then, or maybe a wooden piece like this. Then what you can do, you just wind the wire, the whole wire around this. If it is an wooden piece, then you just take the wood out. So what you get? You just get a coil of wire like this, having turns of equal area, okay, or equal radius, we can say. So all the loop will have the same radius. Okay, okay, so this is a coil. Now what we do, we actually can produce uniform magnetic field with this, using this coil, or we can use electromagnet also. You can just send current through this, then when current passes through this coil, what will happen, a magnetic field, axial magnetic field will produce. Okay, it will produce an axial magnetic field. Okay, so we'll see here in the figure. So when current carrying solenoid, when a current carrying solenoid is suspended by a string, it it orients itself in north south direction. Okay, north south direction of geo of the earth. Okay, of the earth. So this we are seeing. So if a solenoid, like current carrying solenoid, is just suspended with a string, then we can say that the solenoid also orients itself in the geomagnetic, geological north and south pole direction as the bar magnet does. Okay, that means we can see that it has directive property also, directive property or directional property. Okay, property. Now second point is that if you bring one, so if you have one solenoid and bring another solenoid near to it, it attracts or repel. Okay, attracts or repel another current carrying solenoid. Current carrying solenoid, that means which produces magnetic field actually. So current carrying solenoid. Okay, see, in case of bar magnet, we know the similar, like charges repel each other and unlike charges attract each other. So we can say that solenoid also has north and south pole, and each loop or each loop of a solenoid acts as a tiny dipole, magnetic dipole, a tiny magnetic dipole. Okay, tiny, tiny, tiny magnetic dipole. Okay, so each loop will, that means one loop like this. Okay, this if we take, it will actually, so one side it will be north, another side it will be south pole. Okay, in this case, in the given case, see, the left hand side will actually act as north pole. So each loop like this, each loop of a solenoid will act as a bar magnet, tiny bar magnet or tiny dipole moment. See, according to this, see, the north pole is here, south pole is here, north pole here, south pole here, north pole again here, south pole right hand side, north pole, south pole, then north pole, south pole, north pole, south pole. So you can see each will actually produce some magnetic field on the axis, and each, like all of them together, will produce a strong magnetic field. Anyway, so what I was trying to say, or what I was trying to make you understand, that there is a direct analogy, or the solenoid is analogous to a bar magnet. And also you can see the field lines as you draw. Field lines are exactly matching. Okay, for both of them, the field lines, nature or pattern of the field lines will match. Okay, so these are the points of equivalence of a solenoid to the bar magnet. And see, one interesting point here, in case of solenoid, since each turn will act as a bar magnet, if you send them some current, see, the length of the dipole length of the solenoid sometimes reduces. Why is it so? Because each 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 loop will act as tiny dipole. So they will attract each other. Okay, they will attract each other. These loops will attract each other and contract the length. Okay, so these are few points about the equivalence of solenoid to the bar magnet. Now we'll see the axial magnetic field produced by a finite solenoid will be exactly equal to the magnetic field produced by a bar magnet on its axis. So what we are trying to see now, see mathematically, if I show that the magnetic field produced by axial magnetic field produced by a solenoid is exactly same as that of the bar magnet, then I can actually be sure that a solenoid will act as a bar magnet or vice versa. Okay, see, for proving that the magnetic field, see, first of all, for a bar magnet we have got any axial point magnetic field, what we have got, mu0 by 4 pi 2m by r cube, right? R cube, r is the distance from the middle of the bar magnet. So here we'll see the same, whether we are getting the same expression for a solenoid also. So for that, you know, we see I have a compact solenoid where I have a large number of, suppose n number of turns per, or we'll say n small n number of turns per unit length. So this is a solenoid which has length L, and this is the number of turns per unit length, and its area, see, radius is a, and each turn carrying current I. So these are the points. Okay, each turn carrying current I. Now if I consider the midpoint to be O, okay, on the axis, and now I have to find the magnetic field at point P, which is at r distance from the middle point. Okay, middle point O. Now see, I just consider a very small element of length element. Okay, very small element of the solenoid which has this thickness dx, and it is at x distance away from the center. So what will be the magnetic field due to this particular element at P? So that is given by, so magnetic field, I'll just write magnetic field produced by this element at P. Magnetic field produced by the element dx at P is given by dB is equal to, see, this will be mu0 by 4 pi. Actually, for a, see, if I just consider, you know, a circular current loop, what we have seen, magnetic field expression for the magnetic field. Okay, what is the expression we have seen? We have seen the expression is actually mu 0 I into a square, okay, divided by 2 into r square plus a square whole to the power 3 by 2. So this is what we have seen here. I is not only I, here I is mu 0 n into I. N is the number of turns per unit length, and I hope, yes, this is the thing. Okay, so this is the current per unit length. Okay, and dx will be there, then I get the magnetic field produced by dx. Okay, magnetic field produced by dx at a distance r from the center. Okay, now see, I have to find out magnetic field at this point P, not only for this dx element. I have to take all the elements on either sides of O. So I can find out magnetic field, total magnetic field, just by integrating between minus L to plus L, this dB. Okay, that means the mu 0 small n into I, then 2, this let it be there, and also a square. So integration minus L to plus L dx by r square plus a square. I think I need to take this as x square, okay, here, not r square. Is it r square or x square? Just a minute. Actually, I have to take the length. See, this is x, and this is r. Total r is this much. So I have to take the distance from here to here. This will be r minus x. R minus x. So this is what I have to take for this case. This r minus x. Sorry. R minus x whole square. Okay, now see this term. See in case of, okay, I have to make some approximation here. See, if this r is much greater than the a, okay, r is much greater than a, then this term, see this particular term can be approximated as, say, mu 0 ni a square, like this. So here minus L to plus L, this dx divided by, I'll just approximate this part at this condition when r is much greater than the radius. So I can approximate this as r cube only. Okay, 2 r cube. So this is r cube. That means, see, there is nothing to integrate here. Like no term is there. Just dx will be giving you 2l length. Okay, upon integration, that will give you 2l length. So what we get actually here, see, mu 0 n l n a square into 2l divided by r cube. So these are the things. So pi I will just multiply. Here it will be 2. Okay, I'll multiply. See, I'll just write the expression here. Let me write it here. So b I have got mu 0 n I a square divided by 2r cube. So here, if I multiply pi, mu 0, so n I into pi a square divided by, here there will be 2l also. There will be, say, 2 pi r cube. So look, this will be actually, so 2 to just leave, 2 I can cancel also, 2 mu 0. See, I into A means I into area, that means that is actually the magnetic moment. So here there is IAN, so total number of turn will be N into L into N into L into I, that is the total current, and then area multiplied with that. NL pi square divided by R cube. So this is actually M, this part is M, 2 M here mu 0 by 4 pi R cube. Okay, so mu 0 divided by mu 0, so 2M. So this is the final part I'm doing. So mu 0 2M by 4 pi into R cube. So this is actually expression for the magnetic field at any axial point in case of a magnetic bar magnet. Okay, a bar magnet. So that is what we have seen. Okay, so from mathematical point of view also we can show, so the axial magnetic field produced by a finite for a finite length of solenoid, what we see, the magnetic field, axial magnetic field is same as the magnetic field produced by a dipole on its axis. So from this analogy also we can actually say that this bar magnet and solenoid are equivalent to each other. Okay, or a solenoid can act as a bar magnet. Now if a dipole, we have seen in case of electric dipole, here you have a compass needle, as you know it has north pole south pole, so it will have certain magnetic moment. If you place a magnetic moment in a uniform magnetic field, what do you know? It will experience a torque, and that torque is called magnetic torque, given by M cross B. If B the magnetic field, M is the magnetic dipole, so in this case it will be actually M B sine theta. So this is the torque it will experience if a compass needle is placed in a uniform magnetic field. Okay, so this is tau magnetic torque. Now see, uh, using this, we can estimate using this compass needle or oscillation of a magnetic compass needle, we can actually produce the magnetic field around. Suppose I have been given a region where there is a magnetic field, but I don't know what is the magnitude of the magnetic field there. Then I can actually do a simple experiment. See, if I just take a compass needle and I have to just uh, place the compass needle inside the region, okay, where there is magnetic field. Now look, since this has magnetic moment, it will actually experience a torque, right? Magnetic torque. What is that? MB sine theta. MB sine theta, right? And see, if this angle is very small, if this angle is small, then I can actually write this equivalent to theta. You know that. And see, then what we get? MB theta nearly equal to MB theta. So this is magnetic torque experienced by a magnetic needle of compass in a region where there is a uniform magnetic field B. Now, if I just disturb it from this angle theta to d theta, certain angle, you know what it will do? Actually, it will try to come back to its position. It will try to come back to its position. And you know why that happens? That happens because suppose there is a dipole moment of this and mass of this mass of this is m, and I is the moment of inertia. Okay, moment of inertia. Since compass needle is a rigid body, this is moment of inertia. Okay, so now if we just disturb it, it will actually oscillate. It will just oscillate. If we just rotate it by certain angle from this theta, if I just disturb it, it will actually start oscillation. Okay, it will start oscillation in the uniform magnetic field, and that, see, oscillation requires a restoring torque, isn't it? What is the restoring torque? Here, the restoring torque due to this inertia will be rotational inertia. So is given by I omega. L is equal to I omega. So I alpha, torque is I alpha, and alpha can be written as I d2 theta by dt square in terms of angular displacement. Okay, and since it is actually a restoring torque, the direction will be opposite to this TB. I'm just keeping like this. Now magnetic torque will be balanced by this inertial torque. Okay, so TB is equal to minus TR. Okay, at this condition the oscillation will happen. So we get MB theta, and this is I d2 theta by dt square, right? So now I can just do one thing. I can just I can just make this equation like simple SHM. So how we do that? Omega square into theta is equal to 0. I have just written the equation itself. Now let us see what is omega. See here, omega is dt theta. So d2 theta by dt square root of I by m omega. Sorry, mb. That is omega. Okay, omega is the angular frequency of oscillation. So this is SHM, right? So just comparing, this is actually omega is equal to square root of I by m. So we have got the angular frequency of oscillation to be this. So from here I can find out the time period as well. So time period will be 2 pi by omega. That means 2 pi into square root of mb by I. mb by I. Have I done some mistake here? Okay. Let me just check. Okay, omega square theta. Omega is mb by I, not I by mb. This is mb by I. See from here. Okay, this equation. mb by I, square root of mb by I is omega. So 2 pi by omega. So it will be omega is mb by 2 pi. Sorry, mb by I. So 2 pi by omega. Omega will give you I by mb, then I by square root of I by mb. So this will be the time period of oscillation. So if I have a compass needle in a region, and how many times it is oscillating, or what is the time period of oscillation, we will be able to easily find out time period of oscillation. Okay, time period of oscillation will be easily find out, like we'll be able to find out the time period of oscillation of the compass needle. So if we know the oscillation time period of oscillation of the compass needle. See, from there we can estimate the magnitude of the magnetic field. See, here magnetic field is there, here also 2 pi. So look, then I can write t square by 4 pi square I into here. I think there will be mb so excuse me, sorry for the disconnection of the uh, internet. So there was a power cut. I'm back. So what I'll do, I'll just complete this topic here. So experimentally we can find out magnetic field produced by a bar magnet using this time period of oscillation of compass needle. So look here, we'll get 4 pi r square. So t square by 4 pi r square into I here, and this will be t square into m. Okay. So this is the expression. So this is actually a very important expression for finding magnetic field. Obviously, you should remember this particular formula: T is equal to 2 pi root over I by mb. Using this, we will be able to find out magnetic field produced by bar magnet. Okay. Sometime compass needle, like this is moment of inertia of a compass needle. This is the time. This is the magnetic moment of the compass needle. So if these are given, then you will be able to find out the magnetic field. So I just finished with simple potential energy of a magnetic dipole Similar to the electric dipole itself. See, we know the potential energy to theta will be given by work done tau d theta, tau mb into sine theta. So sine theta d theta. If I write t0 to t theta 0 to theta 1, theta 0 to theta 1. So with the minus sign here, mb cos of theta with this limit theta 1. So it will be mb cos of theta 0 to theta 1. Okay, like this. So mb cos there is a potential energy of a magnetic dipole moment is actually given by minus mb cos of theta, or vectorially we can write this as minus m dot b. Okay, this also is possible. Okay, u theta. So you can see from here. Okay, so I think this is not required here. The limit is limit. If you just do this, this difference will be, this theta 0 is 90 degrees. So theta 0 is 90 degree, and this is the reference for the potential energy is 0, and theta 1 is any theta. Then I can write this equation like this. Okay, so u theta equal to this mb cos theta minus mb cos theta, or minus m dot b. Okay, or minus m dot b. Work done, if you need to find out what is the work done will be actually given by u theta. Suppose I am going to theta 2 minus, I was where I was at theta 1. So mb cos theta 2 minus cos theta 1. Here there will be a minus sign, I hope. So anyway, so magnitude of this cos theta 1 minus cos theta 2. So magnitude of this will be the work done. Okay. All right. So we'll stop it here. This part is also similar to this electric dipole itself. So we'll just stop it here for today. Thank you for your patience. Bye for today.